to the major topic of the lecture, which is finding the shear stress, tau, and the angle of twist, capital theta, in closed single cell thin wall tubes. So what this means is if you have a section that has a very large radius, or it doesn't have to necessarily be circular. All right, but the thickness of the section is much smaller than the radius or the diameter of the section. All right. So these, they have an outer surface and an inner surface, and the benefit of tube sections is that, especially if they are undergoing a torsional load, is because they are so they have such a large outer radius, it increases their polar moment of inertia, which would decrease the shear stress in the section. Okay, but they are still very lightweight, so they're able to be light and resist torsional loading. So if we go to the next page, we'll talk about how we're going to define a quantity called shear flow, and we're going to relate shear flow to the shear stress. Okay? All right. So if we have a circular tube, okay, which means we have a constant thickness defined by a mean radius r. So we call this r mean. We'll call this mean radius r mean, which would be equal to the sum of our outer radius plus the sum of our inner radius divided by 2. Here, sorry, I forgot that. That was a typo. All right, and then the thickness of our section would just be the difference between our outer radius minus our inner radius. And then for a polar moment of inertia, we could define our moment of inertia using this equation here, where we subtract the moment of inertia of the outer diameter minus the polar moment of inertia of the inner diameter. So if the thickness is much smaller than the average radius of our section, we can approximate our polar moment of inertia by setting our polar moment of inertia equation equal to this value here. Okay. All right. So these two terms are almost equal once t becomes very close. If t is much smaller than r mean, so we can simplify it and use this equation here now for our polar moment of inertia. Okay. So with this polar moment of inertia term, we can plug it in to our definition of our shear stress, TR over J. If we plug in all of our terms here, we plug in our radius, and we set our radius equal to our average radius of the tube, what we'll end up getting is we'll get this equation for our shear stress tau. Okay. So what we're going to do now is we're going to look at a cross section, and we're going to apply a circular cross section. We're going to apply a torque, and that torque is going to create a shear stress around the section. Okay. So if we look at a small element within that section, okay, it'll have a shear stress, and it'll have the element will have a thickness, which we'll define T, as being the thickness of our tube, and it'll have a length, which we'll call dz. Okay, so what we're going to what we're going to do is we're going to define um, um, we're going to define something called the shear flow for this element, which says that which is going to be the force along our fiber, or the small element here, is going to be we're going to divide that fiber by the unit length. So to relate that to our applied shear stress tau, we can say that if we multiply tau, which is a force per unit area, by the top area of our fiber, so like the top of our fiber here, which would be equal to dz times t, and then the length of our fiber would be dz. We end up getting our dz terms will cancel out, and we're left with that we can define the shear flow as being equal to the shear stress times the thickness. Okay? So for a circular tube, we can plug in our equation for tau here. All right, and we end up getting that our shear flow would be equal to this. Okay.